In this video, we're going to look at two short examples of calculations in inner product spaces. The first example is going to involve polynomials of a degree at most 2, and in the second example, we're going to look at continuous functions on an interval. So for this first example, let's consider 3 polynomials that I have written here. In our inner product space, these polynomials are vectors. And what we're going to do is calculate the inner product of P and Q, the inner product of Q and R, the length of Q, thought of as a vector in this inner product space, and then the distance between the two vectors P and Q. For polynomials of degree 2, we can actually regard them as vectors in the way that we normally would, provided we strip the coefficients away from those polynomials. So for P, that means I'm going to be taking the vector 1, 0, minus 2, where these are the 3 coefficients in front of the constant term x and x squared. Q I'm going to record as 4, minus 2, 1. And R I can record as 0, 1, 2. Then I'm going to use the standard notion of a dot product to evaluate the inner product of P and Q and R. The inner product of PQ then is the dot product of the two vectors 1, 0, minus 2 and 4, minus 2, 1. So that works out to be 4 plus 0 minus 2, which is 2. The inner product of Q and R works out to be 4 minus 2, 1, dotted with 0, 1, 2. And so this is 0 minus 2 plus 2, which is 0. In particular, this means that the vectors Q and R, which are these two polynomials, are orthogonal to each other because the inner product is 0. Now let's calculate the length of the vector Q. The length of Q is the square root of the inner product of Q with itself. So that means we're going to be taking the square root of the vector 4, minus 2, 1 dotted with itself. Because in this example, the inner product really is just the dot product in disguise. So this gives us the square root of 16 plus 4 plus 1. So we'll have the square root of 21. Finally, let's calculate the distance between P and Q. The distance between P and Q is given by the length of the vector P minus Q. And at this point, you can take the difference of vectors or you can take the difference of polynomials. I think I'll use polynomials just to demonstrate that it still makes sense that way. So I'll have polynomial 1 minus 2x squared minus polynomial 4 minus 2x plus x squared. So I'm calculating the length of minus 3 minus 2x minus 3x squared. Again, I need to strip out the coefficients if I'm going to be calculating this inner product. So really I'm taking the square root of the inner product of minus 3 minus 2 minus 3 with itself. So I'm taking the square root of 3 squared plus 2 squared plus 3 squared. So that gives me the square root of 22. And that is the distance between the vectors P and Q in this inner product space. Next, I'm going to look at a different example, the continuous functions on the interval 0 to 1. But I'm going to use a very different type of inner product for this inner product space. The inner product of f and g is the integral from a to b of the product of the functions f and g. This is a definite integral, so out of this calculation will come a number, and that is the evaluation of this inner product. For the specific calculation, let's take f to be x, let's make g equal x squared and calculate the length of f and the distance between f and g. Again, we're going to be looking at an inner product of f with itself. In particular, the length of f squared is the inner product, f. And here we need to use an inner product appropriate to the space, the definite integral. When we use this expression, both f and g are set equal to f. So that means we will be taking the definite integral from 0 to 1 of x times x, because in this problem, f of x is x, dx. So we're evaluating the integral of x squared, which gives us 1/3 x cubed, evaluated at 1 and 0, and so we get 1/3. Now this is all calculating the norm of f squared, and so for our final answer, the length of f, we need to take the square root. That's the square root of the inner product of f with f, so we get the square root of 1/3. Now let's look at the distance between f and g. The distance is also given by a length. That's the length of f minus g. And let's square everything so that we can deal with the square root at the end. The length of f minus g squared is the inner product of f minus g with itself. So what we're really going to be doing is creating a new vector and then pairing it with itself inside of a definite integral. The pairing of f minus g with f minus g becomes the definite integral from 0 to 1 of f minus g squared, because I am pairing f minus g with itself. And you cannot forget to square it in this expression. It's very important. So f and g are not complicated functions here. We have x minus x squared, but now we need to FOIL out these polynomials. And inside the integral, we have x squared minus 2x cubed plus x to the 4th dx. Integrating this, we get x cubed over 3, x to the 4th over 2, and x to the 5th over 5, and evaluating at 1 and 0, this produces 1 over 30. And then the last step is going to be, like before, to take the square root. So this ends up being the square root of 1 over 30.